Okay. Good afternoon, everyone. Okay. Let's see. I'm trying. Well, if you're also doing set theory, you know I was having trouble with my internet connection. So I'm trying a new connection today. You'll see how it goes. Okay. And also before we get started, let's see. I'll just share with you. I've just posted just the first assignment for this course. Okay, so let me share that. Okay, so assignment 1, due next Friday. It's more of like a review assignment or something. Okay, so it's due next Friday at 5. It's annoying. Okay, let's see. So let me share with you the assignment as well. Okay, so for this assignment, of course you can do all the questions, but I only want you to hand in the 1, 3, and 5. Okay. Okay, there's the assignment. Okay. Okay. Okay, so I'm gonna try and get started. And hope for the best with the connection. Okay. Here we go. This is just what we were doing. Is it frozen? Yes, it is. There we go. What is it? The 22nd. Okay. Okay, the things we want to do today. We want to talk about the integers. We want to talk about equivalence relations a little bit. We want to talk about the integers mod n. Let's see. And if we can get through all of that, I'm not sure, but if we can, we'll do more. We want to start review. Just some of the topics from Math 2272. Okay. If we have time today, we'll start that. And I hope we can kind of be done the review and get into new stuff like next week, if possible. Okay. Okay. So before we start, did anyone have any question? Maybe no. Okay. Let me try. Okay, so let's get started with equivalence relations. Well, we need to remember what a relation is. Okay, we'll say a relation, really it's a binary relation, but a relation on A is a subset R, which is contained in the set of ordered pairs of A with A. Okay. Here, maybe I should write lowercase or something. Okay, so I have some set A, and a relation on A is just a set of ordered pairs of A. Okay. Okay. Then if we have A and B, like A comma B in R, instead of writing this, we just write A, R, B. And then if A and B are in A cross A but not R, then we write whatever R is, we strike it out. Okay. And just a quick example might be equality on 1, 2, 3, 4, 5. You just define R to be the ordered pairs where both things are equal. Okay. You know, so I put 3 comma 3 in R because I want this R to represent equality, and 3 is equal to 3. Okay, so this 3, 3, that represents 3 equals 3. Okay. Of course, there's many other relations we can have. We want to study a special kind of relation called an equivalence relation. Okay. When I say study, I just want to review it because we'll see, you know, a bunch of equivalence relations come up in this class. Okay, so let's define what an equivalence relation is. So let A be a set. Let R be a relation on A. Okay. R is called an equivalence relation if, let's see, A, R, A for all A. That's called reflexivity. So the relation is reflexive to for all A and B and A, if A, R, B, then B is related to A, and that's called symmetry. Okay, and the third thing, for all A, B, and C, if A is related to B, B is related to C, then A is related to C. It's called transitivity. Okay. And that's our definition. Okay, I want this to be a little bit more focused or something. I think hope that's a little better. Okay, so we have an equivalence relation. Okay, we need to know that there's a relationship between equivalence relations and these things called partitions. Okay, so first of all, let's just write an example of an equivalence relation. Well, one would be equality on a set. Okay, well, let's do another one. Okay. Just as a toy example, let's do this. This is an equivalence relation. This is an equivalence relation on the set 1, 2, 3, 4. Okay, and you can check that it's symmetric, because if I switch everything, right, like whatever I switch, I get something that's, whenever I switch to the two entries, I get something that's still in R, right? So if I switch 2, 2, I get back 2, 2. So all of these, when I switch them, I get back. If I switch this one, I get this one. If I switch this one, I get this one. So this relation is symmetric. It's also transitive. You know, you can check this. Actually, it's kind of trivial to check that it's transitive. You know, because you have to check that if A is related to B and B is related to C, then A is related to C. This is only like this is automatic if A equals B or if B equals C. So you only have to check when A and B are different and B and C are different. And so the only possibility, the only thing you truly have to check is that, you know, we have 1 and 1, 2 and 2, 1, and we have to check is 1, 1 in the relation and is 2, 2 in the relation, and those are both true. Okay, so it's transitive, and it is also reflexive because 1 is related to 1, 2 is related to 2, 3 to 3, and 4 to 4. So this is an equivalence relation. So and actually for this example, it's much easier to see that, like it would be much easier to kind of group the elements of A according to what is equivalent to what. And if you do that, you see that 1 and 2 are equivalent. Okay. We can group the elements of A according to R as, well, 1 and 2 are both related to each other, so we put them apart. 3 is only related to 3, so we set that aside by itself. And 4 is related to 4, we put that in its own thing. Okay. And these different sets are called the equivalence classes of A. And notice, like, everything in this set is all related to each other. And everything in this set is all the things related to 3. Everything in this set is all the things related to 4. Okay. And notice that if this splits up the elements of A into disjoint sets, okay, we call that a partition. So let's define what, let's define an equivalence class, and let's define a partition, and then we'll say that the equivalence classes will give us a partition of A. Okay. So let's start with equivalence classes. Okay, so let R be an equivalence relation. Okay, let me pause this definition. So let me go back one page. So there's a question, can the equivalence classes have repeating numbers? Do you mean like, like if this is another equivalence class? Okay, no, they can't. The reason is basically distinct equivalence classes, like equivalence classes that are different, can't have any elements in common. So we cannot have some, let me do, like, we can't have something like, here's what can't happen. Maybe on the set 1, 2, 3, 4, 5, or no, maybe on the set 1, 2, 3, the equivalence classes can't be like this. Okay, this won't work, right? Because like this being an equivalence class means that 1 is related to 2. This means that 2 is related to 3. And by transitivity, that would imply that since 1 is related to 2, 2 is related to 3, it would mean that 1 is related to 3. Okay? So because these two equivalence classes overlap in 2, actually they have to be the same. So it really has to be the equivalence class 1, 2, 3 altogether. Okay. So let me now just, yeah, okay. Let me finish defining equivalence classes now, and then we'll try and explain why. Yeah, okay. So we have an equivalence class. Or sorry, let R be an equivalence relation on A, and let A be an element of A, then the equivalence class of A which is denoted with, well, one way to denote it is by square brackets, which is fine. Other ways to denote it are just like, or A bar, I'm sure there's many other ways, maybe like with a tilde, maybe some other ways. Okay. And then this is defined to be the set of all B's such that A is related to B. Okay, so start from A and grab everything that you can, just that is related to A, and put it in a set. That's called the equivalence class. Okay. Okay. And you can, so what we want to show is that the equivalence classes on it given by an equivalence relation give a partition of A. Before we do that, we need to define partition as well. Okay. Let A be a set. A partition of A is a set X of subsets of A of non-empty subsets of A such that, first of all, A is just the union of P and X P. In other words, A can be found by just taking all the elements in the subset, in the elements of X, and joining them all up. Okay, so it's like all the elements A such that A is in P for some P and X. Okay, and the second requirement to be a partition is that distinct for all P and Q in X, with P not equal to Q, you have P intersect Q is empty. Okay, and going back to our example, if I take X to be, well, one of my sets is going to be 1, 2, One of the sets is going to be 3. One of the sets is going to be 4. This is a partition of A, which is 1, 2, 3, 4. And each element of X, these are the equivalence classes of the relation that I defined on the other page. Okay. And I like to think of a partition as just like breaking up a set into like little puzzle pieces or something. But, you know. Okay, so we have partitions and equivalence classes, and these are kind of like there's kind of like there's an equivalence between those two notions. Okay, so like we can write down like a proposition. Okay, let me use this squiggle for an equivalence relation. On A, I have an equivalence relation on A. Then X sub squiggle, which is just the set of all the equivalence classes. This is a partition of A. Okay. And we're not going to prove this, but I think it's worthwhile to just do part of the proof, which is to show why different equivalence classes are disjoint. So basically, or else I guess I should say distinct equivalence classes are disjoint. Okay. So let P and Q be in X sigma with, X squiggle with P is not equal to Q. Okay. And for a contradiction, assume that P and Q are not disjoint. Okay. Now, by the definition of X squiggle, P and Q are both equivalence classes of like some different elements. So also, you can write P to just be the equivalence class of little p, and Q to be the equivalence class of little q, for some P and Q. Now A is in P, so that just means the definition of equivalence class means that P is related to A. So we write P squiggle A. And A is in Q, so Q squiggle A. Okay. Now, we just need a way to prove that P is a subset of Q. So let's let maybe let's let B be in P. So that means that P is squiggle B. Okay, and let me just try and draw a diagram of what's going on. Here's maybe our two different equivalence classes, P and Q. This is A, living in their intersection. And here's P, and here's Q. Okay, and the plan is that we can use transitivity to join P and Q. And so that means P has to be in Q and Q has to be in P. That'll tell us like they're this actually the same. Yeah, let's just do that. Okay, let's skip this. Okay, so Q is related to A, P is related to A. We can use symmetry to say that A is related to Q by symmetry. Now, P is related to A and A to Q, so P is related to Q. That's by transitivity. Okay. And now we just need like a lemma. So if P is related to Q, then the equivalence class of P is the same as the equivalence class of Q. And let me write a brief proof of that. Well, start with P related to A, which is just saying that A is in P. And also, P is related to Q. That's by hypothesis. A is related to P by symmetry. So A is related to P and P is related to Q. So A is related to Q by transitivity. So Q is related to A by symmetry again. Well, that tells you that A is in Q. Okay, so this whole argument tells you that P is a subset of Q. And you can just do the same argument to tell you that Q is also a subset of P. So let me just say this is similar. Okay. So that's the end of that lemma. So it tells you that things that are equivalent have the same equivalence class. And now if we go back to the proposition, since P is equivalent to A, P and A are the same, have the same equivalence class, and also Q and A have the same equivalence class. So P and Q also have the same equivalence class. And that would be a contradiction. Okay. That is maybe a little bit more time than I wanted to spend on it, but I hope that's okay. Okay, and so if you can start with an equivalence class and get a partition. You can also start with a partition and get an equivalence class. So let's, I mean, we can just define that. Let X be a partition, right, of A. And we'll define squiggle X to be a relation on A defined by A squiggle X B if and only if A and B are both elements of some common element of the partition. Okay. Right. So basically, define two things to be equivalent if they are in some common partition of your part, like some common part of the partition. Okay. And then what we get is, so we get another proposition. Let X be a partition of A. Then squiggle sub X is an equivalence relation on A. And not only that, but so not going to prove this. And then not only that, I can start with an equivalence relation, get a partition, and then I can take that partition and get an equivalence relation. And what happens is that these two processes are like inverse to each other. So that is like a theorem. Okay. Right. The map phi from okay, so we can define a function from equivalence relations to partitions, and the rule is just to take an equivalence relation and split A up into equivalence classes, and then this map is inverse to psi and psi tells you to take a partition and find the equivalence relation according to that partition. Okay, so it means, what is this telling us? If you start with an equivalence relation, split A up into equivalence classes, those equivalence classes give you a partition of A. And furthermore, if I then find the equivalence relation according to the equivalence classes, what I end up with is my original equivalence relation. And it also works the other way. I can start with a partition, find an equivalence relation, Find the equivalence classes of that, and that is my original partition. Okay. So it's like we have these two different languages of equivalence relations and partitions, and we have a dictionary which allows us to switch from one language to the other. Okay. Okay, just for the next 10 minutes, let me just remind you about induction. Call this principle of mathematical induction Okay. Okay, so we have for all n greater than or equal to 0, P of n is like some property or statement. And if P of 0 holds, and 2, for all n, P of n, if P of n, then P of n plus 1, then for all n, P of n. I guess it's better to say for all k, P of k implies P of k plus 1. Yeah, that is better. Okay, we have induction. And there are two other forms which I will state. We also have strong induction. And I'll just put strong in quotation marks. It's not really stronger, it's like the same strength, but it's like equivalent to induction, but we just call it strong induction. Okay. Again, we have a property P of n. Okay. Then for all k greater than or equal to 0, how do we say it? We usually say if P of I holds for all I less than k, then P of k. So, so if this holds, then P of n holds for all n. Okay, and that's strong induction, or that's one way to state strong induction. Okay, and then the third thing I'll state is well-ordering principle. Right, and this just says that let S be a subset of the natural numbers and assume S is non-empty. Then S has a least element. Yep. And these three statements, induction, strong induction, and well-ordering principle, they're like, you can assume that they're axioms of the natural numbers. So, and you can use whichever one is like most convenient for you. And so I think on the assignment, question 3 is just a couple of induction questions. So probably we'll take, like, we'll try and work through one of those on Monday in case you need a refresher. Okay. Okay, let's now take just a 10-minute break. Let's just take a break until 1. Okay. Okay, guys, let's start back and kind of want to go through some properties, more things about the integers. The reason why we're doing this part of the review is so that because these concepts we're talking about, we're going to use them like in our examples for group theory and ring theory. Okay. I see that this connection is possibly giving trouble, but please let me know if there's any trouble with the audio. It seemed to be fine for the first hour, and maybe it'll be okay. Okay. Okay, so the first thing we want to define is divisibility. Right. So we're talking about integers. So A divides B if there exists C such that equals AC. Right. So you know, we can say the divisors of 18 are, well, 1 divides 18, 2 divides 18, 3 divides 18, what, 6, 9, 18, right? 1 divides 18 because 18 is 1 times 18. 2 divides 18 since 18 is 2 times 9. 3 divides 18 because 18 is 3 times 6. 6 divides 18 because 18 is 6 times 3. 9 divides 18 since 18 is 9 times 2. And 18 divides 18 because 18 is 18 times 1. Okay, and I guess I should have said the positive divisors. Okay. If I want all the divisors, I can also include all the negatives of these numbers. Okay. And then you have other little tricky things like, you know, you can do a lot of the basic properties. Oh yeah, so first of all, our notation, A divides C means A divides C. Okay, so we use a tall vertical line to mean divides, not division. If I want to write the rational number A over C, or these are rational numbers, different than this. Okay. 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 Because we have this notation of divides, we can define the GCD. Let's do that. Oh, there we go. Sorry about that. Okay, so definition. Let A and B be integers, not both 0. Okay. The GCD, in other words, greatest common divisor of A and B, denoted GCD of A and B is defined to be a positive integer D such that 1, if A divides C and B divides C, then D divides C. So that means, oh, sorry, no, talking about the least common multiple here. I meant to put if C divides A and C divides B. Okay, so that would mean that C is a common divisor of A and B. Then C divides D. So D is a larger divisor than C. The second part is that D is a common divisor. D divides A. B. Okay. For example, the GCD of 18 and 24. That is just what, I guess 6. Okay, and just straight from the definition, the divisors of 24 down, or the positive divisors of 18, and here are the positive divisors of 24. Hope I don't miss any. Okay. And the common divisors are these. And the greatest common divisor is 6. Okay. So 6 is the GCD. Of course, this is a pretty kind of like a useless algorithm. So we have the Euclidean algorithm to help us find GCDs. So we have the Euclidean algorithm. Let me just briefly remind you. Find the GCD of A and B. First, you divide A into B. Okay. Then you divide the remainder into A. Then you divide that remainder into the previous remainder. Divide that remainder into the previous remainder, and just keep on doing that. And eventually you get Rn minus 2 equals Qn Rn minus 1 plus Rn. And then you get Rn minus 1 is Qn plus 1 Rn plus 0. And this is the GCD. Good. Okay, and before this, I should have told you about the division algorithm, but that's okay. Let's just do a quick example. Let's just find the GCD of, say, 1014 and, I don't know, 107. Well, we ask ourselves, how much does 107 go into 1014? 9 times, right? And what remainder do we get? Well, we get 963, I guess 51. Now, this remainder and divided into 107. No, is it really 51? Yes, yes. Okay, now we do 107. 51 goes in twice, the remainder of 5. Of course, now we divide this remainder into 1. We do 51, just plus 1. Now we divide this remainder into this one. So the GCD. Okay. And whenever you find the GCD, you can always find integers x and y such that 1014x plus 107y equals 1. You can do that by back substitution. So let's solve. 1 equals 1014x plus 107y. Well, we do that by back substitution. So first we write 1 in terms of 51 and 5. So 1 equals 51 minus 10 times 5. Now we write 5 in terms of 107 and 51. All right, so 5 is 107 minus 2 times 51. Okay, and now we rearrange everything. So we get 151 plus 2051. So we get 21 51s minus 10 times 107. Now we replace 51 by in terms of 1014 and 107. Then we subtract 10 107s. Okay, so in all we have 21 times 1014, and then we have minus 189, 99, 107. Okay. Okay. And I will probably ask you to practice this. I think one of the practice questions is a question like this. Okay. All right. One thing I have to go back to is the division algorithm. I mean, it is just what allows us to write the sequence of steps. So let me remind you. Okay. Let A, B be integers, and we're going to divide B by A, so A can't be 0. Okay. Then there exists unique integers Q and R. Excuse me. Sorry about that. Okay, so there exists unique integers Q and R such that B equals QA plus R, and 0 is less than or equal to A, or sorry, 0 is less than or equal to R, is less than the absolute value of A. Okay. That's the division algorithm. That's what we use when each step of the Euclidean algorithm is applying this division algorithm. Okay. Now we also have, because we have greatest common divisor, we also have least common multiple. It is just kind of the same definition as GCD, but flipped around. Okay. Let A, B be non-zero integers. The least common multiple of A and B. It's just denoted LCD of, or sorry, LCM. Let me rewrite it. LCM is, it's just the integer E and 0 such that we want E to be a multiple of A and B. E divides E. 2. If A divides F and B divides F, then E divides F. So so E is a multiple of A and B, and of all the other multiples, E is the least one. Okay, so it's the least common multiples. And, you know, let's just find the least common multiple of 18 and 24. Just here are the multiples of 18. Okay. The multiples of 18 are 18, 36, 54. I guess 72. The multiples of 24 are 24, 48, 72. So the kind of smallest thing in both lists is 72. So the LCM is 72. Okay. And just notice 72 times 6, that's what, it's like 432. Is that wrong? That's the same as 24 times 18. Yeah. Okay. Okay. So this is not a coincidence. If I multiply two numbers, I just get the LCM of the two numbers times the GCD of the two numbers. Okay. Okay. And that's nice because I have this nice algorithm to compute the GCD. So it means I don't need an algorithm to compute the least common multiple. I can deduce the least common multiple from the GCD. Okay, so that is good. Okay. Okay. The next thing I want to remind you is of prime factorization. Okay. So let P be integer bigger than 1 if the only divisors of P, the only positive divisors of P are 1 and P, then P is prime. Okay. If n is greater than 1 is not prime, then n is called composite. Okay. And we have a theorem. This is the fundamental theorem of arithmetic. Let n be an integer. Then you can factorize n into a product of prime powers. So P1 to the A1, P2 to the A2, all the way up to Pk to the Ak, where P1, P2 up to Pk are distinct primes, and A1, A2 up to Ak are all integers greater than or equal to 1. And this factorization is unique up to reordering. Okay. So I hope that is just a reminder. See, we need another definition. We're kind of coming to the end of this this section. Just a few more things. Okay. Let n be an integer. We'll just define phi of n to be the size of the set, so the integers such that the GCD of A and N is 1 and A is between 1 and N. Oh, and that's the number of elements of that set. Example. How do we compute phi of 18? Well, 1, we just count, we go from 1 up to N and cross out things that have a common factor with 18. 2, 3 has a common factor with 18. 4 has a common factor of 18. 5 and 18 have nothing in common, have no factors in common except, well, 1. Right? So 8 and 18 both have a common factor of 2. Oops, yeah, 17, 18. Okay, so the things that have no common factor with 18 are 1, 5, 7, 11, 13, 17. There's 4, 5, 6 of them. So 5, 18 equals 6. Okay. And then we have some convenient formulas for computing. First of all, if the GCD of A and B is 1, then phi can split up like this. And the second thing is that phi of P to the A, or sorry, P to the N is just P to the N minus 1 times P minus 1, or N greater than or equal to 1, P prime. So like, for example, if I want to compute phi of 105, well, that's just phi of 3 times 5 times 7. That's just phi of 3, phi of 5, phi of 6. Because 3, 5, and 7 have, like, because 3 and 35 have no factors in common, and 5 and 7 have no factors in common. And then I apply this formula. We get 2 times 4, 6. We get 48. That means that if you were to write down all the integers between 1 and 5 that share no common factors with 105, you would find 48 of them. Okay. Okay. And the last thing in our, just a quick review, is integers mod n. So we start off with the definition. Let's let n be greater than 1, or maybe greater than or equal to 1. Find A congruent to B mod n. So read it like A is congruent to B mod n. modulo n. Why? Well, we just say that A is congruent to B mod n if n divides B minus A. Okay. Oh, that probably went too fast. As an example, 99 is congruent to -1 mod 10. Why is that? Because -1 minus 99, that's -100, which is 10 times 10. So 10 divides -1 minus 99. So that means 99 is congruent to -1 mod 10. Okay. Okay, luckily, this definition gives us an equivalence relation. So we have equivalence classes and things like that. Okay. There's an equivalence relation on the integers. Well, instead of equivalence classes, we'll call them congruence classes mod n. But the equivalence class of A, well, it's just A, and then you have A plus or minus n, A plus or minus 2n, 1. So this is also called a congruence class modulo n. It gets a special name because this is a special equivalence relation. Okay. This is really like part proposition, part definition. Okay. And because we can multiply and add things in the integer, we can do the same thing for congruence classes. Define congruence class of A times congruence class of B, just be the congruence class of AB. Congruence class of A plus congruence class of B, be the congruence class of A plus B. Okay. And part of the proposition is really that these are well defined. Okay. Sometimes sometimes instead of using square brackets, you can also put bars on the A and B. But we'll try and be clear with it. We're doing. Okay. And finally, We'll make a definition. We'll define UN to be those congruence classes such that you have an inverse for some C. Okay. Oh yeah, and I forgot to give you the symbol for the set of equivalence classes mod n. We just call it Z mod NZ. Okay, equivalence class. Let's see. On Monday, we'll do some examples of these kind of problems. Well, this is called modular, and we'll do some examples on Monday. Let me at least try and do get started with a review of group theory. Yeah, let me get started. Right. Okay. A group is a set G equipped with a binary operation times such that 1, there exists an identity element. Okay. There exists an identity element 2 for each x in G. There exists x inverse. Such that x times x inverse is x inverse times x equals E, 3, x, y, z. We have associativity. Okay, and that's a group. Okay. Examples of groups. Well, this is the reason why we introduced the integers and all that. We did all that review because that's going to be one of our examples. One, the integers with and the binary operation is addition with addition. 2. The integers mod n is another group. Under addition, well, the addition is modulo n. It's another example of a group. And lots of other examples. Real numbers. Of real numbers. Any vector space. With whatever vector space you have, take the addition to just be the addition of vectors. Okay. And there are many other examples of groups which we'll get to, but for now, notice like these all satisfy an additional property. They satisfy like the additional law that the group, like the order can be switched. Okay. Okay, so a group G is commutative. If x times x for all x and y. Okay. Or actually, I guess I should say abelian. Sorry about that. Okay. And then for all the examples I listed, the group law is more naturally thought of as being addition. So sometimes we will write, x plus y instead of xy, 0 instead of e, negative x instead of x inverse. Okay. To give you an example where we use multiplication, another example, I guess I should call this S. Think of all the complex numbers whose modulus is 1. Right? And this is a group under multiplication. Okay. Okay. And then we'll see lots more examples next week. And I think we're going to stop there. I'm going to try and continue the review with a few short videos so that we can use the in-class time to just work through problems. Also, if you if I was ever breaking up, please send me an email or something. I would like to know if the audio was if it was fine or it was coming and going.